rotation properties of rotation matrices continue. If A, B, C belongs to SON, it may be SO3, SO2, etc. The closure property, AB is also in the group. That is A rotation matrix, B rotation matrix, then AB is also rotation matrix. Associativity, AB into C, that is A into BC. Identity element existence, there exists an element I in the group such that for every A into I equal to I into A equal to A. Inverse element existence, there exists an element A inverse in the group such that A into A inverse equal to A inverse into A equal to identity matrix. Propositions 3.3, the inverse of a rotation matrix R belongs to SO3 is also a rotation matrix and it is equal to the transpose of R, that is R inverse equal to transpose of R. We know that transpose of R into R equal to identity matrix implies R inverse equal to transpose of R, obviously. Since determinant of transpose of R equal to determinants of R is 1, so transpose of R is also a rotation matrix. Here consider two rotation matrices in 2D. For example, A is cos theta minus sin theta cos theta, and B is cos alpha minus sin alpha tan alpha cos alpha. If we multiply it AB this way, finally we got cos of theta plus alpha minus sin of theta plus alpha, sin of theta plus alpha, cos of theta plus alpha is also a rotation matrix. You should know this formula, trigonometric formula. Now, proposition 3.4, the product of two rotation matrices is a rotation matrix. Proof. Given R1, R2 belongs to SO3, their product R1, R2 satisfies R1, R2 transpose into R1, R2. It must be an identity matrix. We check it. Applying property R2 transpose into R1 transpose, order reverse into R1, R2. Then after R2 transpose into R1 transpose into R1, that is I into R2. I is neutral. So R2 transpose into R2. R2 is rotation matrix, so it must be I. And determinant R1, R2 equal to the property determinant R1 into determinant R2. But R1, R2 rotation matrices, so determinant is 1. So 1 into 1. So determinant of R2 1, and this is I. So thus R1, R2 satisfies the condition for rotation matrix, so it is also a rotation matrix. Proposition 3.5, multiplication of rotation matrices is associative. R1, R2 into R3 equal to R1 into R2, R3, but generally not commutative because of R1, R2 does not equal to, may not equal to R2, R1. For the special case of rotation matrices in 2D, SO2, rotations commute. This one AB equal to BA. Propositions 3.6. For any vector X belongs to RQ and rotation matrix belongs to SO3, the vector Y equal to RX has the same length as X. The proof, mod Y whole square, that is transpose of Y into Y. One is rotation, one is row matrix, the other is column matrix. But Y is replaced by Rx. So Rx transpose into Rx, that is X transpose R transpose Rx. But R transpose into R is identity matrix. So X transpose into I into X, that is X transpose into X, that is mod X whole square. Done.